We're going to look at reactions, both for the formation of ether and the reactions that ethers undergo in this online lecture. The first thing to realize about ethers is that ethers are really very stable. They're resistant to a lot of chemical reactions. The only kind of chemical reaction that they really undergo, significantly so, is the cleavage reaction with acid, to cleave them with acids. So realize that ethers are a relatively stable functional group. To synthesize them, we're going to see that we can do two reactions. We can either condense them or we can do an SN1 or SN2 substitution reaction to form an ether. The condensation is shown below, and because you have to use acid, the conditions are not really for anything other than just the simplest alcohols. What we do here is we basically use acid to remove water, and anytime that you join two compounds by the removal of water, it is called a condensation. So you can see here that we have ethanol. On this side we have ethanol. What are we going to do? We're basically going to remove water. You see how I am circling the molecules that would make up water. So we're cutting this bond, and we're going to cut this bond, and when we do, we join the pieces together. And what does that give us? That gives us water and an ether. Okay, this is not the mechanism. Basically, the mechanism is that the alcohol group is protonated, and then this other alcohol acts as a nucleophile to after the protonated alcohol leaves, and then the oxygen is deprotonated. I don't expect you to know the mechanism, but some people like to see the mechanism so they better understand. So the book has the mechanism in there. You can take a look at it. For more complicated ethers, what we do is we use a Williamson ether synthesis. To make an ether in this manner, we have an alcohol that we form into the alkoxide. There's a lot of ways to do it. What's shown here is sodium hydride forming the alkoxide, but we can use sodium amide or we can use sodium metal, and both of those will end up giving us the alkoxide. The alkoxide then can do an SN2 on a primary alkyl halide. The primary alkyl halide allows the oxygen to come in and displace the leaving group, and it ends up giving us an ether. Notice, this is an SN2 reaction, but what happens if the alkyl halide is not primary? If the alkyl halide is not a methyl or primary, what happens is E2 will predominate, and you'll get an alkene and very little of the ether formed. So we only use this for a primary alkyl halide. So now you see these two ethers. How can you form these? By the Williamson ether synthesis. Well, to figure out this first one, what you do is you go and you look at this side, and you see that the oxygen in the ether is connected to a secondary carbon here. Then we look at this side, and we see that this carbon attached to the oxygen in the ether is primary. Because you must have a primary alkyl halide to do a Williamson ether synthesis, we must make this carbon into our alkyl halide, and this will be our alkoxide over here. So, for the SN2 to work properly, we have to use this alkoxide on the secondary carbon and this alkyl halide on the primary carbon. Let's look at this one. How could we form this? Well, we do the same process again. We see that this is a tertiary carbon, and we see that this is methyl. A methyl alkyl halide will work quite well with an alkoxide doing an SN2 on it. So we make this part of the molecule, the entire molecule with the oxygen, into an alkoxide, and we choose our substrate to be methyl iodide or methyl bromide. Notice, because this is tertiary, we actually could do another type of reaction. If you remember back in chapter 7, I believe it is, where we learned about SN1 and SN2, you would see that tertiary alkyl halides can undergo solvolysis reactions with alcohols. So we could actually have taken the alkyl halide here and dissolved it in a lot of methanol, and that would have given us an SN1 reaction, and it would have formed that product. Ethers will undergo acidic cleavage. How do we cleave them? We cleave them with a strong acid, and typically we choose a strong acid that has a good nucleophile on it. Why? Because some of these reactions go through an SN2 reaction, and some go through an SN1, and we're going to see how to differentiate between which one is occurring. If I look at this reaction shown here, you can see that what is the hydrobromic acid going to do? It's going to cleave this and put a hydrogen on the oxygen and then a bromide on one of the carbons that was in the ether. If I look at this, this is going through an SN2 mechanism. Let's go through the SN2 mechanism down here, and then we'll go back and look and see why cleavage occurs the way that it did up here. Ethyl isopropyl ether can be cleaved with hydroiodic acid. Right here is the mechanism for the protonation reaction. So we get a proton transfer by the oxygen reaching out and grabbing the proton, and then the electrons jumping onto the iodine and forming iodide. So this is the product, the protonated oxygen, and here's the iodide. This is now a good leaving group. A good leaving group with an iodide. The iodide is going to go and do an SN2 because this is secondary and this is primary. So it's going to go ahead and do a fast SN2 on this primary carbon, and then this will be my leaving group. That gives me the isopropyl alcohol over here and an iodoethane. So what we do when we're looking at an ether and we treat it with hydroiodic or hydrobromic acid, we look at it and we say, can an SN2 occur here? Well, you can't have an SN2 occur here. It would be extremely slow. It wouldn't go. But this carbon can do an SN2. So this oxygen becomes protonated, and this will be my leaving group to form phenol. And then the bromide is going to come in. The bromide actually comes in and displaces the phenol as a leaving group, and I end up getting the bromine on the less hindered carbon. Notice this. If a tertiary carbon is attached to the oxygen in an ether, the mechanism is going to be SN1 and not SN2. So we're going to see that if SN1 occurs with the tertiary halide, with the tertiary carbon, the halide ends up on the tertiary carbon and the alcohol group will be on the other. But if there's no tertiary carbon, the mechanism is SN2 and the halide ends up on the less hindered carbon. That's like what we saw in the previous slide. We saw SN2 occurred because SN1 could not occur. There was no tertiary halide, tertiary carbon on the oxygen. So this is the mechanism if there is no tertiary carbon. What happens is the oxygen gets protonated, and then the halide is going to do an SN2 on the least hindered carbon. Here, both the carbons are the same, and so there's no difference. But if there is a difference, you choose the one that is going to be the least hindered. So if the ether is a combination of primary and secondary carbons on the ether, here's an example. This one's primary, and this one is secondary. The mechanism is going to be SN2, so this part becomes the alcohol, and this part becomes the halide. Why? Because this carbon is less hindered. Now, if the ether has a tertiary carbon, then you have to look for the SN1 reaction that will occur fastest. So let's look at this ether right here. We can see this is tertiary, this is secondary. So what happens? This oxygen becomes protonated and this group leaves as the alcohol. That forms a carbocation here, and then the bromide adds there. So we get the tertiary halide. Even if one side is primary and this is tertiary, still the SN1 reaction is faster. So when this is protonated, the leaving group leaves and you make the alcohol, and then the bromide comes into the carbocation. So here's the mechanism if there is a tertiary carbon. If there's a tertiary carbon, what you see right away is that the oxygen gets protonated. That makes the oxygen into a good leaving group. Because now there's a tertiary carbon, the SN1 occurs very fast, and that leaves as a leaving group. So we get the primary alcohol here. Now the bromide dives into the carbocation and forms the alkyl halide. So we end up getting the tertiary alkyl halide whenever there is a tertiary carbon in the ether. Now it's your turn to try it. What would be the product of hydrochloric acid cleaving methyl cyclohexyl ether? Well, if I look at this, I have methyl, a primary, and cyclohexyl, a secondary. There's no tertiary here, so we're going to end up getting the methyl chloride and the cyclohexyl alcohol, cyclohexanol. What is the product of hydrochloric acid cleaving methyl T-butyl ether? Well, if I look at this, methyl is primary and T-butyl is tertiary. So we're going to end up getting the methyl alcohol and the T-butyl halide. So we get methanol and T-butyl chloride.